Assalamu alaikum, dear students. This is the first lecture of your course Structural Analysis 1 CE 301T, and this course comprises of 4 credits. Now, first we will discuss about the course contents, which are like you have 5 units in this course, which includes Unit 1 Introduction to Structural Analysis and Basic Concepts of Structural Analysis. Then the unit second is the determinate structures. Unit third is bending and shear stresses in beams. Unit fourth is slopes and deflections. And unit fifth and the last is analysis of columns. Before going further, I would like to make you familiar with the contents in the chapters we have. First unit is Introduction to Structural Analysis and Basic Concepts of Structural Analysis, which includes the definition of structure, structural engineering, history of structural engineering, structural analysis, structural forms, simplification of for purpose of analysis, types of loads, specification of a force, free body diagrams, equation of equilibrium, condition equation, displacements, compatibility, boundary condition, principle of superposition, stiffness and flexibility. Then we have the unit 2, which is determinate structures. It includes introduction to the determinate structures, bending moment and shear force in determinate beams, three-hinge arches, determinate beams with overhang and a propped cantilever with a moment hinge. Then we have unit third, which is bending and shear stresses in beams. It includes flexure formula, bending stress and shear stress diagrams for homogeneous beam section of various shapes and composite sections. Then we have slopes and deflections, which has slope and deflection of determinate beams by double integration method, by moment method, by conjugate method, and by energy methods. Then we have Castigliano's first energy method and application to simple determinate trusses. Then we have the fifth unit and the last unit, which is the analysis of columns, which includes stresses in columns, short and long columns, buckling phenomena, Euler's and Ranke's theory of crippling load, stresses in eccentrically loaded columns. Now is the unit 1, which is the introduction to the structural analysis and basic concepts of structural analysis. As you already know what are the contents of this chapter. Now we will know what is a structure actually. Structure, it refers to a system of connected parts used to support a load. It's actually an assemblage of load-bearing elements in a construction. While designing a structure, we need to serve a specified function to serve to the public use. The engineer must account for its safety, aesthetics, and serviceability, while taking into consideration economy and environmental constraints. Once the preliminary design of a structure is proposed, the structure must then be analyzed to ensure that it has its required strength and rigidity. And to analyze a structure properly, certain idealizations must be made as to how the members are supported and connected together. And the loading which comes on a structure are basically determined from codes and local specification, which you will know in the further classes. And the forces in the members and their displacements are found using the structural analysis. We have a natural structure in front of us, which is the best or the marvelous example. That's the human skeleton, which consists of several substructures, which include skull, which is a fine shell structure providing sturdy protection to soft brain. Then we have a rib cage, which is a fine 3D frame structure. We have numerous bones, which are like frame structure, interconnected by the pin joints, and we have the flesh clad on the Skeleton, non which is a non-structure except for the muscles and tendons which contribute to load resistance. Then is the structural analysis. Structural analysis is a mathematical algorithm process by which the response of a structure to specified load and action is determined. The response is measured by determining the internal forces or stresses resultant and displacement or deformation throughout the structure. It also defines the manner in which the various forces acting on the structure gets transmitted. And as the building height and weight increases, this we have to take into consideration, the lateral load due to wind and earthquake comes into play, increasingly in addition to the usually gravity load. And in those circumstances, we have to take care of these lateral loads also and design as per the need. Then we have the things on which the structural analysis depends. First is the behavior of the structure, how it behaves, what are the conditions, what are the extreme conditions that it has to face, and then is the geometry, what kind of geometry do we have of a structure, and then the material properties, the material that we use, whose properties are to be whose properties are to be seen first to meet the needs of the structure. Then we have the connections at the various joints, and finally the loading of the structure. What kind of a load? What type of a load does the structure have? All the site on a design. Support connections. The most common type of support connections that we have to deal with in this semester are pin joint, ridge joint, and a roller joint. First, we will discuss pin joint. Pin joint, it basically permits free relative rotation between the interconnected members, ensuring translation is same. And here the bending moment is always zero at the pin joint locations. Translation degree of freedom arrested, but the rotation of connected members can occur freely. Here I will show you how a pin joint is usually seen. In this connection, we have a translation support reaction, that is the vertical support reaction. For example, this is AY, and we have a horizontal support reaction which is usually denoted as AX. X is in the X direction and Y signifies that it's in the Y direction. It basically permits the relative rotation between the interconnected members while ensuring that the translation is the same. The freedom to rotate release the possible transmission of bending moment. Hence the bending moment is zero at the pin joint location in all the connected members except when the external moment is applied at the joints. Now is the roller support. It always allows freedom for rotation as well as horizontal translation. The translation degree of freedom arrested in one direction. Freedom to translate freely along the plane of the roller direction and also for the connecting member to rotate freely. It's usually drawn as like this. Here you have only translation support reaction, that's A in Y, in the Y direction. Now we have the fixed joint. It basically is that kind of a joint which does not allow any relative rotation between the connected members. It's also called as ridge joint or the moment resisting joint. Here all the 3 degrees of freedoms are arrested. There is no translation movement, there is no rotation possible. And it's usually drawn like this. this is a fixed joint. Here you can show a beam like this. Here all the three here all the rotation as well as the translation support reactions are restricted, so we have three support reactions here. Often it's misconstrued that a ridge joint implies no deformation. It must be clearly understood that the rigidity here refers only to the joint. The structure itself is deformable. The rigid joint can translate and rotate, but it will do so always ensuring compatibility of displacement of the ends of the connecting elements at that joint. Now we would like to know what is a beam, because in this course you have to learn how to deal with the beam, how to analyze a beam, different types of beam, which are uniformly distributed loaded beam, simply supported beam, cantilevers, and so on and so forth. The structural member that resists external load by bending, which results in the development of an internal force resultant, that's called bending moment. Beams are primarily designed to resist bending moment. However, if they are short and carry large loads, the internal shear force may become quite large, and this force may govern the design. Now, what kind of loads do we have to deal in this course? They are like, we have various types of load that we have to deal with. First one is the uniformly distributed load, which you might be knowing how are they distributed on a beam, which I can show you with an example. For example, we have a beam here. It's supported on a roller joint and a pin joint. That's a simply supported beam. And the loads are like this, uniformly distributed throughout. The intensity is same throughout the beam. Now, then we have the triangular load. This is usually shown like this. We have a simply supported beam. It's rested on a roller support and a pin support. And triangular load, it varies uniformly like this. Then we have point load. Point load is usually shown like this. You have a simply supported beam, again same roller and a pin support, and its load is concentrated at the midpoint or at a distance of A from point A and B from point B. Then we have the trapezoid load, which usually shown like this. Same beam rested on a pin joint and a roller joint, and trapezoidal loads are shown like this. The intensity varies. Then we would like to know what's all about displacement and compatibility. The basic method for the structural analysis is the flexibility method, which is also known as the force method, and the compatibility method. And then we have the stiffness method, which is also known as the displacement method and equilibrium method. We will discuss all these methods in our next classes. Now, you before moving further, you should be knowing what a free body diagram is. It's actually, if a member is selected, it must be isolated from its supports and surrounding, and its outline shape drawn. All the forces and couple moments should be shown that act on the member, and the forces common to two members act with equal magnitude but opposite direction on the respective free body diagram of the member. And in a planar structure, there are three independent equations of equilibrium, as you already know from our previous lecture or from the previous slide, there are three independent equations of equilibrium for the overall free body, in which the support reactions are exposed, plus three additional independent equations for every cut. Remember this, for every cut there are three additional independent equations for the free body diagram of the structure, in which the internal force resultant at the cut section is exposed. Then we have the equation of equilibrium. What's equation of equilibrium? Here the structure or one of its member is in equilibrium only when it maintains a balance of force and moments. And this requires that the force and moment equation of the equilibrium be satisfied along three independent axes. That is, the force into x direction, summation of forces into x direction equal to 0, summation of force into y direction equal to 0, summation of forces into z direction equal to 0. And we have also the moments there. That is, summation of moments in x direction, in y direction, as well as in the z direction should be equal to 0. But as we know that the principal load carrying portion of most structures lie in a single plane, and since the load are also coplanar, so the above moment requirement for equilibrium reduces to summation of forces in x direction equal to 0, summation of forces into y direction is equal to 0, and summation of movement in z direction equal to 0, which you will understand with the help of an example. We have a beam here which is supported on a pin joint from the extreme left side and a roller joint on the right hand side, and there is an overhang also on this beam. You have an inclined load on this beam 60k at an angle of 60 degree, and you have a moment also the distances are 10 feet. The distances are like this: 10 feet, 4 feet and 7 feet. Now first of all we will draw a free body diagram for this beam. You have a roller support which will be shown, the support reactions will be shown as this: By here at point A, Ay and Ax. You have load here which we have to show like this now, because as the figure shows that 60k force has to be resolved in x and y component, and the 7 feet dimension line is not needed since a couple movement is a free vector and can therefore act anywhere on the beam for the purpose of computing the external reactions. So this is 60 sine of 60k, and this is 60 cos of 60k, and you have a moment here which is 50k ft. Now we have to check out for the equation of equilibrium. Equilibrium. Firstly, summation of forces in x direction should be equal to 0, where this is the positive direction. That gives out Ax minus 60 cos of 60 is equal to 0, which gives out AX is equal to 30k. And then we have summation of movement at A, where this is the positive direction, equal to 0, which after solving gives out minus 60 sine of 60 multiplied by 10 plus 60 cos of 60 multiplied by 1 plus by multiplied by 14 minus 50 is equal to 0, which gives out by is equal to 38.5k. Now the third equation of equilibrium is summation of forces in y direction equal to 0, whereas this is the positive direction. Which gives out minus 60 sine of 60 plus 38.5 plus ay equal to 0. Solving the equation, we get ay is equal to 13.4k. Hope you have understood how to calculate for the equation of equilibrium and how to draw the free body diagram.